My name's Owen Majors. This is Honors Unit 2 project. The element I chose was neon, and neon is, the symbol for neon is Ne. The atomic mass is 20.1797 atomic mass units. The atomic number is 10. Neon is a noble gas and is a non-metal type. It's very light, very inert gas. The physical properties of neon: it's colorless. Under low pressure, it glows a bright orange red if an electric current is passed through it. It's a gas, and so the phase change, neon changes from a gas to a liquid at a temperature of negative 245.92 degrees Celsius, or in the English system, negative 410.66 degrees Fahrenheit. It changes from a liquid to a solid at a temperature of 248.6 degrees Celsius. Neon is an odorless gas, a tasteless gas, and the density is low at 0.89994 grams, and it is soluble in water. Now, on the other side, the chemical properties of neon include: the oxygen will not react with neon in typical conditions. Neon is chemically inactive. Under low pressure, it glows a bright orange red if an electric current is passed through it. This brings me back to the point that neon's use is really just for lighting, because it brings a bright color, bright orange red, and it grabs attention, and so it's usually used for maybe advertising and things like that. Lastly, neon is a lightweight element. It's a noble gas, and the density is very low. The compound I chose was carbon dioxide, or CO2. Carbon dioxide is bonded by a covalent bond. Frozen carbon dioxide evaporates at room temperature without passing through a liquid phase and is known as dry ice in its solid form. Carbon dioxide is heavier than air, colorless, odorless, and has a freezing point of negative 55.6 degrees Celsius. Carbon dioxide is soluble in water, acetone, and ethanol. It's widely used in many industrial processes that require large-scale refrigerating, particular freezing and chilling of foods. So, as we know, carbon dioxide is vital to survival of plant life because of the process of cellular respiration. And as we know, carbon dioxide is a waste gas. So, it's produced by the combustion of fossil fuels, or as we know, gas you put in cars. Now, what makes this compound different than a mixture or an element is because a mixture keeps its own properties, while CO2 has properties different from the elements it contains. And it's not an element because elements are, every atom is that element, while CO2 is carbon and oxygen atoms. It's not uniform. But to answer the question, can this compound be chemically separated, and if yes, explain how? Well, CO2 is a little tricky, you see, because carbon dioxide, it can be physically separated, but it's a closed chemical cycle. So you get what you put into it, or like a battery, you have to charge it so much, and you get that much charge out of it. Scientists actually found you can split the compound with a laser, but it is very difficult to split the compound due to the double bond it has between its atoms. All in all, the amount of energy it takes to split the bond is so high, it makes splitting the compound inefficient. Heterogeneous mixtures, aka suspensions. I chose sand and water, like the beach. You have your ocean water and the sand that is sunk to the bottom because it's insoluble. But you may ask, what about all the sand that touches my leg when I walk into the water? Well, that's due to the waves and movement. because if you give it time and it was settled, like if you put sand in a water bottle, it would sink to the bottom, because this mixture can be separated because they separate after time. Besides habitat for marine life, sand and water could be used for marine construction in the real world. For example, sand and water, a construction company may make a path to a certain destination they need to get to fill in a hole with sand, because it is better for that environment, since the marine life uses sand and it's part of their ecosystem. It's not like they're filling it up with cement or anything poisonous. Now, suspensions differ from colloids and solutions because they're more than 100 nanometers, aka they're bigger than the other two. The particles are going to be bigger, and it's going to be cloudy. The appearance is cloudy, unlike solutions. It's heterogeneous, often opaque, but it can be translucent. It separates and settles, unlike the other two, and the particles do not pass through filter paper, unlike the other two. The solution I chose was Kool-Aid. Kool-Aid is sugar, water, and flavor powder. To create this Kool-Aid, the sugar dissolves in the water when it's heated and it changes color. This is a homogeneous mixture, so it cannot be easily separated, but it can by means of evaporation. So if you let the can or glass of Kool-Aid out in the sun, eventually, or if you tried to boil it, eventually the water would evaporate and you would get gross Kool-Aid. But the mixture is used in our world as beverage or hydration. The sugar and flavor powder is the solute, while the water in this solution is the solvent. The last mixture I will be talking about is a colloid. Now, the colloid I chose was liquid air salt, which is obviously going to have liquid, and it's a pressurized can that is meant to spray this liquid. Now, this mixture can easily be separated through a filter and is used for things like hair products, pest control, and an example of these would be hairspray and Raid. Well, it could also be used in the painting business for spray paint or graffiti. And these all have a mixture that has to be able to grab onto the target, so having a Tyndall effect is needed to aim the aerosol can. Even though the Tyndall effect will be a great identifier of a colloid, it is not always going to be a colloid if this mixture displays a Tyndall effect. But some key indicators that the mixture is a colloid is that the particle size is going to be medium between a solution and a suspension. Unlike a solution, it's going to be cloudy, but like a suspension, also cloudy. It could be homogeneous or heterogeneous, and it's often translucent and opaque, but it can be transparent. And the particles do not separate, unlike a suspension, but like a solution, and it does pass through filter paper. Done by Owen Majors.
You still here? It's over. Go home. Go.